Hello. Previously, we have covered the first energy storing elements for electrical circuits, which were the capacitors. And today, we will start covering our second energy storing elements for electrical circuits, which are the inductors. After learning the constituent relationships for current through and voltage over an inductor, we will learn the energy storage in inductors, and afterwards we will learn how to find the equivalent inductance value for series and parallel inductors. An inductor is a circuit element that stores energy in a magnetic field. An inductor can be constructed by winding a coil of wire around a magnetic core, as shown here. In this case, we have a copper wire wound around some type of ferrite core. Inductors are represented by a parameter called the inductance. The inductance of an inductor depends on the size of the inductor, material used, and method of construction. Assume we have an inductor consisting of length L with a cross-sectional area of A with N turns of wire and some specific magnetic core from a specific material. Then the inductance value of this inductor is given by mu times N squared times A over L, where N is the number of the turns. And this number is usually very high for some of the inductors. It might be N is equal to 1000. A is the cross-sectional area of the core in square meters. L is the length of the winding in meters, and this might be very, very long. And when this is very long, in addition to the inductance value, actually we start to have an internal resistance of the inductor. And secondly, mu is a property of the magnetic core known as the magnetic permeability. The unit of inductance is Henry, abbreviated with the capital letter H. Magnetic permeability actually consists of two terms, as it was the case with the dielectric permittivity. And we have firstly the term vacuum permeability, mu0, which is equal to 1.25 times 10 to the minus 6 henries per meter. And secondly, we have the relative permeability, mu-r, which changes for different materials. Usually air, concrete, vacuum, and Teflon has the relative permeability of 1. But we have some special materials such as the mu metal, which might have the relative permeability of 50,000. That is why this material is used for magnetic shielding of electronics. This material, mu metal, consists of nickel, iron, copper, and chromium, and has this very high magnetic permeability value. The voltage V across the coil or inductor is proportional to the rate of change of the coil current, and it is given with this mathematical relationship. V is equal to L di over dt. So for resistors, inductors, and capacitances, you need to memorize these relationships for solving circuits. The inductor current IT can be found by integrating the inductor voltage from time minus infinity until time t, and according to the mathematical expression is shown here. I is equal to 1 over L, an integral from minus infinity till t, v tau d tau, tau being a dummy variable for the time. Remember, the current through an inductor is given with this integral, which is from time minus infinity till time t. Often, we don't know the value of the current at t is equal to minus infinity when the Big Bang was happening. So, therefore, we need to use an initial condition. Let us show this mathematically. I will divide my integral into two parts, one from t0 till t and another one from minus infinity till t0. However, for the second part here, I will simply write the current through the inductor at that time instant as an initial condition. Since the current through an inductor is an integral relationship, this cannot change instantaneously. The voltage over an inductor can change instantaneously. However, the current cannot. In this exercise, we need to find the voltage across an inductor with the inductance value 0.1 henries when the current in the inductor is given by I of t is equal to 20t times e to the minus 2t amperes. This is actually a very simple question. We need to use this relation. V is equal to L di over dt. The only slight complication is how do we find the derivative of this expression here. And for that, we have the product rule for the derivatives. So if a function consists of two functions in the form of u times v, then we find the derivative of that function, which is written as a product of u and v as u times dv over dx plus v times du over dx. Now, here in my expression, I can define u as this part and v as this part, and let us use this in order to find my derivative. V of t will be equal to L times, which is 0.1 times di over dt, which is equal to 0.1 times, in parentheses, 20t times the derivative of b, which is minus 2 times e to the minus 2t, and the derivative of u, 20 times v, which is e to the minus 2t. I can simplify this a little bit. It will be 2 times minus 2t times e to the minus 2t plus e to the minus 2t. And I can simplify this a little bit further. It will be 2 times minus 2t plus 1 times e to the minus 2t. This is my final expression for v of t. So as you can see, from now on, in order to solve these questions, you need to know calculus very well, because we will be using integrals and derivatives and later the solution of differential equations very frequently. Now let us figure out what is the energy stored in an inductor. The power is, as always, P is equal to V times I, voltage times current, and the voltage over an inductor is equal to L times di over dt. Therefore, the power over an inductor is L times di over dt times I. The energy stored in an inductor is stored in the magnetic field. Assuming that at the time it0, the current is equal to 0, the energy stored in an inductor can be found as an integral from t0 till t, p d tau, and this will be equal to L times an integral from it0 till it, I times di. Accordingly, when we do the mathematics, we realize that the energy stored in an inductor is very similar to the energy stored in a capacitance. It is 1 over 2 times L times I square. In the case of a capacitance, it was 1 over 2 times C times V squared, the voltage square. An inductor, similar to a resistor and also capacitor, is a passive element. It cannot generate energy. It can also not dissipate energy like a resistor, but it can store an energy and then release it afterwards. Now we need to find the energy stored in the inductor at t is equal to 0.2 seconds. And we have the function v is equal to 10t times e to the minus 5t volts for the voltage over that inductor. And the inductance value is equal to 0.1 henries. And another piece of information given is that the current is 0 for t is less than or equal to 0. So basically I know as the initial condition at t is equal to 0 that current is equal to 0. Here we first need to find the current from the voltage equation, which is given as V is equal to 10t times e to the minus 5t. So for that, I will need to take an integral. For taking this integral, I will use the integration by parts formula, and accordingly, my integration will be this. I of t is equal to 1 over L. 1 over L is 10. 10 times integral from 0 till t v d tau plus I0. But I know that I0 is equal to 0. So I will simply take this integral 10 times integral 0 to t, 10t times e to the minus 5t d tau. So instead of t, let us write the dummy variable taus here. And accordingly, what will be the result of this integral? I have x times e to the power of ax dx is equal to this expression here. So let me try to do this without messing it up. 100 times an integral with the bounds here t and 0 minus e to the minus 5 tau divided by 25 times 1 plus 5 tau. I think that I did it right. Now I need to plug into this expression the t 100 times, I will put a very big parenthesis here, minus e to the minus 5t divided by 25 times 1 plus 5t. And I will subtract from this expression when I will put the value of t is equal to 0. And here I observe that I will have minus 1 over 25. Let's close this parenthesis and try to simplify this expression a little bit further. Then according to this will be 4 times in parenthesis 1 minus e to the minus 5t times 1 plus 5t. So this is my expression for the current I of t. Now I have the general expression for the current IT for this circuit, and now I need to find the energy stored in this inductor at t is equal to 0.2 seconds. I will do this by first defining the current at 0.2 seconds, which will be equal to 4 times 1 minus e to the minus 1 times 1 plus 5t 1 amperes. Now I will go to the MATLAB and solve this expression. You can use your scientific calculators, and accordingly I will be at 0.2 seconds 1.057 amperes. Once I have this, I need to find the energy stored in this inductor at t is equal to 0.2. So this will be accordingly 1 over 2 L times I 0.2 seconds squared. And this will be 1 over 2 times 0.1 henries times 1.057 squared. And accordingly, this is equal to 0.0559 joules. So this concludes the solution of my problem. Let us figure out what is the equivalent inductance of a series of inductors. Here I have inductor 1 in series with inductor 2 and so on and so forth up to inductor n. So in this case, the equivalent series inductance value is equal to the summation of all the inductors. Let's figure out how to do this. So I will simply write the Kirchhoff's voltage law for the circuit. V is equal to V1 plus V2 plus ... plus Vn. And accordingly, V is equal to L1 times di over dt plus L2 times di over dt, because the same current is passing over all of these inductors plus dot 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 Ln times di over dt. Let us collect all the L terms, and I end up with L1 plus L2 plus plus Ln times di over dt. I can write this term as the L parallel and write it in a more compact form using the summation operator. I is equal to 1 till capital N L subscript I, and this is my equivalent inductance for multiple inductors connected in series. And in the case of the parallel inductors, we have this relation here. 1 over Lp is equal to the summation of 1 over Li, I from 1 to N. It's very similar to the parallel resistances. In order to derive this relationship, you should write the Kirchhoff's current law for this node, which we'll leave right now as an exercise for the more interested students. Now we need to find the equivalent inductance of the circuit, and I will imagine that all the inductors are resistors and reduce them, but then remember that they are all inductors. So I have 3 millihenries in series with 4 millihenries. So accordingly, this is 7 millihenries, exactly the same as the resistors. Now I have 42 millihenries in parallel with 7 millihenries, and this will be equal to 1 over 42 plus 1 over 7, which is equal to 42 times 7, 294, divided by 42 plus 7, 49, and accordingly 6 millihenries. So then my whole circuit reduces to, I need to learn how to make the inductor sign. 3 millihenries, 6 millihenries, and 5 millihenries, all of them in series to each other, and accordingly I will add these three values. 3 plus 6 plus 5, 9, 14 millihenries. So basically the equivalent inductance value is L equivalent 14 millihenries for this question. Now in this question, we are given the voltage of the voltage source as an exponential decay, a quite fast one with minus 20t, and the current entering this source as minus 1.2 times e to the minus 20t minus 1.5 amperes. We are provided the initial inductor current, and we are asked for the L and R values. So I think I will start solving this question by writing the Kirchhoff's current law around this node and see what happens. Alright, now here this current I is entering this node, this current IR is getting out, this current IL is getting out of this node as well, and here in this node, due to this voltage source, I have the voltage V, assuming I have the reference node here. Now I think I will start by finding what is IL as a function of t, which can be found using this relation 1 over L integral from 0 to t v tau d tau plus IL0. Let's write everything which I know. 1 over L integral from 0 to t. The equation for v is given here. 4 times e to the minus 20t, not t here, the dummy variable tau, just to be on the correct side, d tau, and we should not forget the minus 3.5. Note that this minus 3.5 is outside of that integral. Let us not get confused. Let us take the integral. 1 over L in parentheses e to the minus 20 tau divided by minus 5 with the integration bounds of t and 0, and here I have minus 3.5 as well. Let's try to figure this out further. I will write 1 over 5L times e to the minus 20t with a minus sign, minus plus 1, minus 3.5. Let's try to write this in a neat way. Actually, it's already in a very nice form. I will write 1 over 5L times 1 minus e to the 20t minus 3.5. Here I found my expression for IL as a function of t and also as a function of L. Now I will write Kirchhoff's current law for the node V. So current I is entering, I is minus 1 over 2 times e to the minus 20t minus 1.5, which is equal to V over R. This is IR. So 4 times e to the minus 20t divided by R plus this expression here for IL. 1 over 5L times 1 minus e to the minus 20t minus 3.5. Let us simplify this expression a little bit. Minus 1.2 times e to the minus 20t plus 2 is equal to 4 over r e to the minus 20t plus 1 over 5L times 1 minus e to the minus 20t. I actually only added 3.5 to the both sides. Now this looks rather intimidating and it appears as if we have a single equation but two unknowns. The unknowns are R and L. However, here is the trick. In these type of circumstances, it is always useful to evaluate the system at extreme conditions. Namely, at t is equal to 0 and when t goes to infinity. At t is equal to 0, we will have minus 1.2 plus 2 is equal to 4 over r plus this whole expression will disappear because 1 minus 1 will give 0. So this whole thing goes out. So now I can calculate r. R will be equal to 0.8 is equal to 4 over r, and from here I have r as 4 divided by 0.8 as 5 ohms. Now, how will I find L? Let's try to evaluate this expression at t goes to infinity. What will we have? All of these exponential terms will converge to 0 because it is e to the minus 20 times a very big number. So I will have only terms with constants. Minus 1.5 is equal to 1 over, oh no, just not minus 1.5. 2 is equal to 1 over 5L. From here, I will calculate L as 2L is equal to 1 over 5, and from here L is equal to 0.1 Henry. And I found both my R and L values for this question by evaluating the state of the system at t is equal to 0 and t is equal to infinity. So here the plots represent the voltage and current of an inductor in the circuit, and we need to find the value of the inductor. Here we will be using this relationship, V is equal to L times di over dt. However, we need to understand that di over dt here is a constant because the current is changing as a linear equation. So let us try to find the slope of this curve. S1 will be equal to delta I divided by delta t, which is 3 amperes divided by 4 milliseconds. And this is equal to 0.75 times 10 to the power of 3 amperes per second, which is equal to 750 amperes per second. That's the slope. Now, let us write this equation in a different way. V is equal to L times slope I. From here, I have L is equal to V divided by slope I. V here is 30 volts. 30 volts divided by 750 amperes over seconds is equal to, I will write this in millivolts, 30,000 millivolts divided by 750 amperes divided by seconds is equal to 40 millihenries. So we found the value of the inductor as 40 millihenries.